What if I told you this coin could power a city? Not because it's radioactive, not because it's special, but because it has mass. Today, I'm going to explain one of the most mind-bending ideas in physics, why mass and energy are actually the same thing, why moving fast makes energy explode, and why nothing with mass can ever reach the speed of light. Before Einstein, we thought we understood energy pretty well. If something moves, it has kinetic energy. The faster it moves, the more energy it has. We even had a formula, Ke equals to 1 over 2 mv squared. Double the speed, quadruple the energy. It was for everyday life. Cars, baseballs, humans. This works perfectly. But then physicists started asking a dangerous question. What happens when something moves really, really fast? Like near the speed of light. Einstein showed that the total energy of a moving object is E equals mc squared over square root 1 minus v squared over c squared. Now, don't panic. You don't need to memorize this. Just notice one thing. That square root in the denominator. As v gets closer to c, that denominator gets smaller, which makes the energy explode. At the speed of light, the energy would be infinite. That's the wall of the universe. Now, here's the craziest part. What if the object isn't moving at all? Set v equals to 0. The formula becomes E0 equals to mc squared. That's Einstein's most famous equation. It means, even sitting perfectly still, mass is already energy. You don't need motion. Mass is stored energy. Now, let me explain that E equals mc squared formula even deeper. Suppose you're watching a cat float freely in empty space when suddenly it emits a flash of light in all directions. The light carries away some energy. We'll call it E. So by conservation of energy, the cat must have lost energy E. But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy from the light come from? Never mind that now. Let's imagine you get bored and zoom off in a spaceship in the middle of the experiment. But from your news perspective, you're sitting still in your spaceship and the cat is the one moving past outside the window. Therefore, you'll calculate that the cat has some kinetic energy of motion, and when you see that the cat emit the flash of light, you'll again measure that its energy decreases by the end of the light. Except now that you are moving, special relativity tells us that time passes at different rates for you and the cat, so you'll measure at a different value for the frequency and thus the energy of the flash of light. This is the relativistic Doppler effect, and for our purposes, it amounts to multiplying the energy of the light by plus 1 your velocity squared divided by twice the speed of light squared. So to recap, if you take off at velocity v, you'll see the cat gain some kinetic energy, Ke1. Then at the flash, you'll see the cat's energy decrease by E times 1 plus v squared over 2c squared. On the other hand, if you wait, you'll see the cat's energy decrease by E, and now when you take off, you'll see it gain kinetic energy, Ke2. But this is silly, you never touch or otherwise influence the cat in either case, so you should get the same total energy by the end. Rearranging, we said that the kinetic energy before and after the flash must be different, and the kinetic energy of an object is 1/2 of its mass times velocity squared. But we know that the velocity was the same in both cases, so in order to account for the difference, the cat's mass must change when it emits the flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must equal the energy divided by c squared, or, as you heard before, E equals mc squared.
So now that we understand where the mass energy equivalence formula comes from, let's put this to practice. So the first question we have is a system loses 2 grams of mass. Calculate the energy released. So what are we given? We're given that the mass is equal to 2 grams, right? And 2 grams, let's put that into kilograms. That would be 0.002 kilograms. And now remember our formula. We'll put E equals mc squared to find the amount of energy released. So our mass is given because again that's our 0.002 kilograms, right? So let's write that in. So 0.002 kilograms. And then our c is also given because that's just the speed of light, which is 3 times 10 to the power of 8 meters per second. And remember to add the square. Next, let's multiply this all out, giving us 1.8 times 10 to the 14 joules. So this basically shows that 2 grams of mass can produce that much energy. Let's move on to the second question. A nuclear reactor produces 9 times 10 to the 14th joules of energy in 1 day. How much mass is converted to energy in 1 minute? So let's start off by finding the amount of energy that we can make in 1 minute. So we do this by having energy minute equals the energy you make in a day over 24, because there's 24 hours in a day and 60 minutes, we do divide by 24 times 60. So what this gives us is basically the amount of energy produced in a day is already given in the question right there, right? So 9 times 10 to the power 14 joules over 1,440, which is just 24 times 60. So multiply this out and it gives us that number. That's how much energy the nuclear reactor produces in a single minute. Split this into a formula by rearranging the mass energy formula. So we get M equals E over C squared. So we already know these values and we just need to find the mass. So let's just plug them in. Mass is equal to energy you get in a minute over C squared, which is just the speed of light squared again. So here we can plug them in. And what this all divides up to is 6.9 times 10 to the negative 6 kilograms. So basically what this is telling us is that the nuclear reactor can convert 6.9 times 10 to the negative 6 kilograms of mass into energy per minute.
With how cosmic of a scale Einstein's mass-energy equivalence principle may seem, it might be surprising just how many real-life applications it has. In nuclear fission, a heavy nucleus like uranium-235 absorbs a neutron and splits into two lighter nuclei. The products end up with slightly less mass than the starting nucleus, and that mass defect becomes energy, first as fast fragments and radiation, then as heat. Power plants capture that heat to make steam and generate electricity, and the same high energy density is what enables nuclear naval propulsion. In PET medical imaging, a radioactive tracer emits a positron, which quickly meets an electron. They annihilate, converting their mass into energy as two gamma rays emitted in nearly opposite directions. PET scanners detect those paired photons and use coincidence timing to reconstruct when the annihilation occurred, producing maps of metabolic activity widely used in cancer diagnosis and monitoring. In radioactive decay applications, unstable nuclei release energy because their decay products have a lower total mass. That released energy is directly deposited in tissue in radiation therapy and targeted pharmaceuticals, and it's also used outside medicine, for example in sterilizing medical equipment and performing industrial radiography to inspect materials and welds. Ultimately, Einstein's mass-energy equivalence principle is not just some abstract hypothetical physics. It has had real-world applications since its discovery and will continue to do so.